Okay, let's go ahead and get started with the lecture today. And today we're going to continue where we left off last time, which was looking at interprocess communication. But we're going to add a few more types of interprocess communication today. And as a quick reminder, we've looked at a couple methods, or several methods, for allowing processes to communicate with each other. And the reason we need to have those ways for those processes to communicate with each other is because they have their own, they don't have shared global variable space. They're not living in the same memory space. They're completely isolated from one another by the operating system. And because of that, we need to have some more sophisticated way for them to communicate with each other. And we looked at doing that previously with queues, pipes, and managers. And those queues, pipes, and managers gave us a way to essentially create mechanisms by which we could communicate from one process to another process. And in this case, we're not dealing with threads, we're dealing with processes which are completely isolated. We have this way of getting them to communicate with these three methods. We're going to add a few more today. So today, or last time, we also mentioned these value array objects, C-types, sockets, and some other kind of frameworks that allow that to happen. We're going to look at a few of those today. Specifically, what we're going to look at is these value and array objects, C-types, and we're not really going to look in detail at C-types. We're also not going to look at sockets. We'll leave that for later. But we're also going to look at a new thing that's part of the standard Python library that's a shared memory object that kind of does some of the work for us so we don't have to deal with C-types directly. So let's start off with value and array objects. So value and array objects, they're built into the multiprocessing module. And it has a special class called value, just like this. So there's a special class that's already built into the multiprocessing module that we can use, and it works like this. So basically we say multiprocessing.value, we give it some type code, and then here's this set of arguments we could pass in to this. The first parameter is one of the C-types type codes, which means we can make that value integer or floating point or really any C-type that we want, and we'll look at the C-types that are available here in a second. And then the second parameter is an argument list to be passed on to the constructor of that type. So in other words, this gives us the ability to initialize the values of these type codes. And what this returns is this shared variable object that we could then use in multiple processes. So let's look at that in a little more detail. So here are some examples of creating value instances. So here, this num equal multiprocessing.value. I put this lowercase d in quotes, and then 0.0. D is a decimal or a double precision float, so that d is not a decimal integer like it is with %d in the printf statement if you're used to C. This d is a decimal value that's a double precision float. And there's the value that I'm initializing it as. So this num object now is now an object that can be shared between multiple processes. Here's another one. Here's creating an integer. Counter equal multiprocessing.value. I is for integer. 0 is the starting value. So that initializes that shared variable as 0. Now, once a value instance has been created, it can be accessed by multiple processes as a shared memory variable, meaning we can then just do the name of the variable dot value. So num.value equal pi would set that decimal integer or that double precision float to 3.1415926. And then counter up here, there's counter.value plus equal 1. We can access that through that. So, and multiple processes could then access that, and it will handle locking out or handling the mutual exclusion for writing or reading those values as they're modified or read or rewritten. Now, there are other possible type codes besides D and I that we looked at here. So let's take a quick look at the type codes that are available. And really, all of the basic types that you'd have in something like C is available there. So character is C, B is a signed character or a byte. Capital B is an unsigned character. The U is a Python Unicode. That's a Unicode character. H is an unsigned short. Capital H is a signed short. Capital H is an unsigned short. I, and you'll notice that there's a difference here. The capital letters are the unsigned version. The lowercase letters are the signed version. That continues down here. So there's a long, or a int, a long, and a float, and a double. So note that U type code corresponds to Python's Unicode character. That could be 2 bytes or could be 4 bytes depending on what kind of build that you're on for Python. But anyway, note that there's a whole host of these things that we can actually create of this value type. Now, those single value variables can then be shared across those multiple processes. One will update it. It'll automatically then be updated in the other process as if it were a shared variable. Now, it also turns out that to make things a little more useful, rather than just single variables like that, you can also make an array. And an array here, it works the same as we did before, except we use multiprocessing.array. And that's built in as well. That's part of the multiprocessing module. And you give it a type, and then you give it a size. In this case, range 100. We'll make an array of 100 integers or daily values. We give it 365. That makes an array of 365 double precision values. And then once those are created, you can just index them in the way you would access a normal kind of array or list. So shared array subscript 10 plus equal 5 will add 10 to that location in that. Now note that these are not like normal Python lists. You can't change the type of elements once they've been created. In other words, they're kind of like statically typed arrays that you would see in C. And the reason for that is the array module, just like the value or array object, just like the value array class, just like the value class, they're built on top of these C language types. Now, you can't change the type, you can't add and remove items. In other words, you can't append, you can't delete. You basically just have a statically allocated array. If you do want to have an array that is dynamically adjustable, you should use a manager, and we talked about that at the end of last lecture. So go back and look at class 12 for that. But one of the advantages of using this multiprocessing.value or multiprocessing.array, one of the advantages of using those classes is that they're very efficient because they're built on top of a shared memory model of the operating system itself. All right, so here's a complete example of sharing that value between 2 different processes. And just like we did with shared synchronization mechanisms up here, we have some function that's going to do something to counter.value. Down here in main, we make the value, so we have to do that inside of this name equal main guard, so we only get one of these created. So we have one shared variable called shared val. And what we're going to do is we're going to pass that to the processes. So here I created 10 processes. Each of those I pass this shared value to those, so they all have access to this shared integer value that starts out at 0. And each one starts, and they all go in here, and 10 times they add 1 to it. And since I have 10 processes, adding that 1 to it. So each one is incrementing counter.value 10 times. There are 10 of them, so we'd expect there to be 10 times 10, 100 as the final value when that's done. And this will print that. Now the cool thing about that shared value is that that's all we have to do. We can access it inside of the thread as if it were just a normal variable, counter.value plus equal 1. Now, you would expect that with 10 processes, each increment 10 times, you'd expect that we should get an answer of 100. But here is the output when I ran it. It never came out to be 100. So what's going on there? And the answer is that these shared variables don't have any synchronization around them. They're really just shared memory, just like a shared variable would be in a thread. Just because they're in processes doesn't mean that it can do that. So in other words, even though access to the value itself is guarded and locked out, when I do a plus equal 1, it has to fetch the value into the Python interpreter of one process, push a 1 on the stack, cause an add operation to add those, and then cause a store operation to store that back into this value. So while accessing this is atomic or protected, doing an operation on it like this is not. And let's actually talk a little more about that. So what's going on here? Why didn't we get 100? So according to the Python documentation for multiprocessing.value, a new recursive lock object is created to synchronize access to the value. So the assumption that a beginning programmer might make is, hey, it's already synchronized. I don't have to worry about protecting access to that object. It's locked automatically during accesses, so I don't need to have a lock or a semaphore or any other kind of synchronization mechanism. And the question is, well, if the object is locked, then why do we have a problem? And the answer to that is what I said just a minute ago. The problem is that the automatic lock that surrounds access to the value is very finely grained. In other words, it's only grained around fetching the value or writing the value, not getting it, doing some operation, then restoring it. So when we perform an operation like this, counter.value plus equal 1, in our code, access is not performed in an atomic manner. It's not performed all at once. In other words, if we were to look at what this is actually doing, the sequence would look like this. Acquire the lock, get counter.value. So that now we have counter.value. The Python virtual machine or Python interpreter would then add 1 to that value that it retrieved, which now knows we're no longer locked. And then once it's added 1 to that value, it needs to restore it. So it acquires the lock, stores the value, and releases the lock. But notice there's a span of time here and here where somebody could change that. So why is that a problem? Well, multiple processes can lock and get the same value. They will then all add 1 to that same value, and then they could at the same time lock and update or acquire the lock again, update to the new value, but we've lost the fact that there were 2 of them doing that. So that's a typical concurrent update problem, just like we saw way back in lecture 1 or 2 whenever we did the ornamental garden problem. Or a whole host of other problems, things on the midterm, whatnot. So how do we fix that? And the answer to that is we need to add our own lock that we manage and surround this entire access to that. So even though it's acquiring access, a lock to access the value at this level, we need something a little broader scope than that to protect it while we're actually retrieving it, changing it, and then updating it. All right, so here's how we're going to fix it. In our main up here, we create a lock, a single lock, and we're going to pass the shared value and the lock to each of the threads. Now that they have a lock, we're just going to use with lock around the thing that's updating it. So now we've protected this as a critical section, this whole thing. And at that point, now we have a solution. So that implementation there will work and we'll get 100 every time. So again, just be cautious. Just because it has synchronization built in to protect that value during accesses and updates, it's not broad enough to handle something like this. So it'll lock, get the value, unlock, but then we're unlocked while we add 1, and then we're unlocked when it restores it back to that again, or locks again and restores it. But we need to protect it for the entire duration of this whole line. Okay, further improvements to this. Well, that implementation works. It does rely on the processes, however, to use the lock properly. In other words, we have this shared variable. We're relying on the processes to know that they need to lock and they need to, while they're accessing that thing. So there might be different processes that need to access some shared data, and they might not know to lock. They might not use the lock properly. So we have to either rely on them to do the right thing, or we're going to have problems again, and that will be bad. So as soon as we have one access to that shared variable that's not protected in some way, then we have a problem. So how do we protect that? Well, the way we can always protect it is to go back and use that monitor concept that we had talked about previously, where you protect the value in a class and then make accessor methods to change it or modify it in some way. And by doing that, we would then have a protected way of accessing that value. And let's look at doing that. So here, we're going to make our own shared value class. And inside of that, we're going to make a lock, and we're going to make a value. And then, to add to it, we use the lock. To get value, just to read it, we don't really need to protect that because this is atomic anyway. But notice, to add to it, we do that. And then we would just use that in our main program like this. Here's the shared value class that's protecting for us. And now here we're doing, we're passing that into this function that we have here, the shared value. And since that shared value there is one of these classes, not the shared memory, this is kind of the class that's protecting that shared memory. And now when we access it, we do shared value.add or sv.add, like we are in here to add 1. So rather than doing the plus equal here, we're doing that inside of this class, so it's always protected. And now any process we make, as long as we require them to use this class to access the internal attribute value, will be good. There's no way to misuse that by going through the class. Okay, so quick summary of value and array types. Value and array objects allow us to create kind of this shared memory object that can be accessed across multiple processes. Even though they don't have global memory themselves, it's kind of abstracted away, and the multiprocessing value class or array class handles all of the synchronization behind the scenes and communication between those processes. So objects by default have automatic locking to ensure. I don't know why it says unsure. Let me fix that. Ensure. To ensure that access and update operations are performed in a mutually exclusive manner. So by default, they already lock, but it's at a very atomic level. So we need to make sure to lock that ourselves if we are doing something that will be dangerous in any other kind of concurrent solution. So be cautious that if you're doing something other than just a quick access to read a value, a quick access to update a value, if you're doing something like incrementing it or pulling it out, doing an operation and then restoring it, you have to add your own synchronization. And so we have to be cautious, perform our own synchronization where explicitly needed. And we need to do that to ensure safety and liveness properties of our solution are preserved. And again, what's the difference between safety and liveness? Safety is where something can get a corrupted value. Liveness is where something can either deadlock or live lock or have a starvation condition. So it's up to us to add the synchronization to make sure that we preserve these. It doesn't happen by itself just because it automatically locks just to read the value or update the value. Now, and again, to reduce the chance of issues happening, I usually like to, whenever I have some concurrent object like that, use that monitor concept where you're building a kind of accessor shell or a monitor around the data to protect it through any of the accessor methods. So if we have shared memory, got to be careful. All right, now there are what are called shared C types, which kind of are that same thing where you can make C language compatible blocks of data. Really, that's kind of behind the scenes what's going on in these value and array objects that we already talked about. And that's what I say down here, that's essentially what's behind the curtain when we use value and array objects. It's just doing that for us. You could do it directly, but this is really considered not, it's a lower level way to do the same thing we can already do with these, so it's a little less abstracted. Maybe you would want to do that, but I'm not going to cover it in detail here. And the other reason I'm not going to cover it in detail here is starting with Python version 3.8. The multiprocessing module introduced a mechanism for directly accessing allocated blocks of shared memory without having to go through C types or these things up here. So we're going to spend just a little bit of time looking at those. And that is the multiprocessing.shared_memory. So that new submodule, this is actually a module inside of multiprocessing. Notice this isn't capitalized. This isn't a class. This is a separate module that's part of the multiprocessing module or inside of the multiprocessing module. But what that allows is us to allocate and manage memory blocks that are truly shared between processes. And here's a description from the documentation. This module provides a class, shared memory, for the allocation and management of shared memory to be accessed by one or more processes on a multi-core or symmetric multiprocessor machine. In this module, shared memory refers to System V style or System 5 style shared memory blocks, though is not necessarily implemented explicitly as such, and does not refer to distributed shared memory. Now, let me just talk about that for a second. Or actually, let me finish reading it and then we'll talk about it. It says, this style of shared memory permits distinct processes to potentially read and write to a common or shared region of volatile memory. In other words, RAM. Processes are conventionally limited to only have access to their own process memory space, but shared memory permits the sharing of data between processes, avoiding the need to instead send messages between processes containing that data. Sharing data directly via memory can provide significant performance benefits compared to sharing data via disk or socket or other communications requiring the serialization, deserialization, and copying of data. So in other words, the advantage of one of these shared memory objects is performance. But note that it does not allow us to do distributed shared memory. In other words, this has to be on one machine with the processors are accessing the same RAM. It allows them to both access that same block of shared memory between two or more actual processes in a way very similar to what would happen with two threads that are in the same process space. But if there's two completely separate systems, like a network cluster or a cloud computing based system, then where it's multiple machines with their own RAM, you can't really share things because it's not based on message passing. It's based on sharing the same block of RAM in the same place. So this one changes it, that one could see it. This one changes it, that one could see it. They're just, imagine two workers or two people sitting in front of a whiteboard and they can both write on it and they can both look at it. But it's not a different copy and this person makes a change and it sends the copy to the other end. It's not like that. It's literally memory that's shared between two processes. All right, so that new feature allows us to allocate and use truly shared memory, which can be a significant performance improvement because we don't have a bunch of overhead with sending data back and forth. Now, there's some useful classes in there. The main one is multiprocessing .shared_memory.shared memory. And notice that is a capital S. And notice that we give that shared memory a name. There's also this create equal that starts off as false, and there's the size that we want it to be. But basically, the way that works is when you create an instance of this one of these shared memory objects, it creates a new shared memory block or attaches to an existing shared memory block. Each shared memory block is assigned a unique name. In this way, one process can create a shared memory block with a particular name, and a different process can attach to that same shared memory block using that same name. Now notice this is actually pretty cool because it doesn't require both of those processes to necessarily be started by the same parent process like we saw earlier where we had to pass that to that. In this case, you can just make a shared memory block, give it a name, tell it to create it, and then other processes can be run even later, days later, open up, access that shared memory block, and close. So the idea here is that we're creating that, giving it a name, and then other processes can then access it by the name. And again, since it's one copy being accessed by multiple processes, it can be incredibly fast. Okay, so let's look at that. It says a resource for sharing data across processes. Shared memory blocks may outlive the original process that created them. When one process no longer needs access to a shared memory block that might still be needed by other processes, the close method should be called. When a shared memory block is no longer needed by any process, you can call the unlink method, and that will basically get rid of it. So in other words, you could have a process that runs, creates a shared memory block, and then closes. And then you can make another process that runs later that opens up, attaches to that memory block that already exists by name, and then when it's done, it says, well, I don't need this anymore, nobody needs it anymore, so unlink it, and then the operating system will get rid of it. And this was something that was added, I believe it was mentioned on the previous page in System 5 of Unix, but it also works on other operating systems like Windows. It's just implemented in a different way, not using the Linux or Unix methodology for doing that. And shared memory actually became part of the Unix standard POSIX, so any Unix-like operating system has followed that, and really Windows has kind of started to, years ago, had started to copy a lot of the stuff that was in Unix, so they have a similar way of dealing with that. Now, one thing to note, create controls whether a memory block is created or an existing one is attached. So if we're the main process, we usually would create that as true, and then in a new process that then needs to attach it would then connect to it and set that as false, which is the default. Now, size specifies the requested number of bytes, so you can think of that a lot like the malloc function call, but we're allocating a size for that. And this is in bytes, not in integers or something else, so we would have to then do that. So if we're attaching to an existing one, it already has a size, we don't need to specify the size, it's ignored if we do. Okay, so how do we access one of these once it's been created? Well, once we have that object, when we've attached to it or created it, then one of those shared memory objects .buff gives me kind of a byte block view of that memory, or a memory view of the contents. The name can access the unique name of it, and size can access the size. So really, once we want to access the memory, we would use that shared memory object .buff to access the buffer that's there. And again, once the size can't be changed dynamically, once it's been created, you can attach, you can read how big it is, but you can't make it any bigger. Okay, so here's an example that does that. And here I have this, in this case I've created this process where I created a shared block. And in this case, I'm saying create equal false here in the sub-processes. But up here in the main, I'm creating a shared memory thing. I'm naming it mem1, saying create equal true, giving it a size, num items, which in this case is just 20. So I created a block of 20 bytes. And then I create a lock as well. I'm going to pass the lock to all those processes so they can lock, access it, and unlock. We still have to do that, our own synchronization when we access this. But essentially what this is doing is it's taking two random places in that and it's swapping them. So this is kind of a way of shuffling, think of like shuffling a deck of cards, but rather than doing it with just one process, I'm setting up and creating, in this case, 20 different instances where each of them 10 times is going to swap things around. So it's a way to more quickly shuffle up this block. But one thing to notice here is notice I don't have to pass the shared memory block to this function because we access it by name. In this case, mem1. We do have to be a little bit cautious though, because some other process could be using the same thing. So if you name it something like mem1, it's possible another process could also name that thing mem1. So a common technique for naming these is to use like a time stamp code, like read the value time.time, make that the name of the thing, and then since we could store that in memory between these two things or pass it into that function, we could access it. But you might also name it the name of the process or the name of the use of it, high scores, whatever you want it to be. Just be cautious because since it's accessed by name, you could have two different processes try to access the same thing with the same name that are not related to each other. Okay, so to use this shared memory buffer, since it is just bytes, we need some way of placing structured data into it and pulling that structured data back out. One of the primary ways of doing that is using the pack and unpack module or functions that are in the struct module, and that allows us to encode data in a structured way and decode it. So I'm not going to cover struct, pack, and unpack in detail here. You can learn more about it on your own. But if you want to stick things into that, struct.pack and unpack can be used to deal with things like a structure would be in C. So you could have It can also deal with arrays. So you could have an array of, I don't know, 10,000 integer values. You pack that, put that into the shared memory buffer. Another processor wants to read that, unpacks it, and then accesses it, makes changes, repacks it, puts it back in, and so forth. So that essentially packs and unpacks the data for you. You could also access it yourself without using pack and unpack, just using kind of the index into that, just like the array object we saw earlier. So you could do that as well. Now, there are a couple other shared memory classes that are useful. There's what's called a shareable list. And a shareable list, essentially, it provides a mutable list-like object, just like lists in Python are, where all values are stored within that are stored in a shared memory block. That constrains storeable values to only the int, float, bool, and string, bytes, and none built-in data types. So you can't have other object types, but you can have anything that's ints, floats, booleans, meaning true and false, strings, bytes, and none data types. Now, it also differs from the built-in list type in that those cannot change their overall length. So in other words, there's no append and insert. So even though the list itself is mutable, you can't change the length of the list itself. You can change the elements of that list, but you can't add another one to it or take one away. So they also don't support kind of the dynamic creation of new shareable list instances via slicing. So you couldn't take an existing shareable list and then cut it down and get another shareable list out of that. And again, they're accessed by name, just like the other shared memory is. Now, the shareable list, when you create one, it actually has a count, the number of there are some methods. You can do count, which returns the number of occurrences of some value in that list. Index, which returns the index position of the value that we ask for. Format, it's a read-only attribute that has the struct packing format used by all the values that are stored in it. And then there's SHM, which is the shared memory instance where the value is stored. So this is the equivalent of that buffer we saw earlier in a shared memory object. It's just called SHM, stands for shared memory. That's kind of the buffer version of all of this stuff. So this shareable list is really similar to a buffer where it's packing and unpacking for us when we access it. And notice that's easier to do because we don't have to do it ourselves. It does it for us. All right, so quick summary here. Sharing memory between processes, in other words, using multiprocessing.shared_memory is both good and bad. The good thing is it's fast since data isn't being sent back and forth between the processes, just multiple processes sharing the same physical piece of memory. That's especially good when we need to share a large amount of data, because if we had like a million items, we don't want to be sending a million items back and forth, because it's going to be really slow. But having a million items and multiple processes accessing that, kind of like imagine a database with a whole lot of elements in it, and people need to connect to the database and search through it. You don't want to have all those processes have to make an entire copy of the entire thing. You want them to fire up, access the shared memory, find what they need, report that back to the owner or the process that was looking at that shared memory, and then close out and be done with it. The shared memory is especially good for things like that. Also, it's kind of cool that you can access the blocks by name, so you could make different named blocks do different things. You're not limited to just one shared memory block. You could have dozens of them. You could have the player data, the high score data. You could have the world data that's in a shared memory thing with a massively multiplayer game, for example. And it's extremely fast since they're just physically sharing the same memory. Now, the bad thing, it's a little more difficult to control since the processes are actually accessing shared memory, which means we have to be careful and use synchronization. So because the memory itself is actually shared, we need to use synchronized methods to access that. And we have to do that ourselves. Also, it's bad in the way that storing complex data in a shared block of memory can be non-trivial. In other words, we have to use that pack, we have to use unpack, and so forth. And also, since the data is shared in local memory, transitioning that source code that uses that to a cluster or a distributed computing model with like a cloud-based system with existing across a whole range of machines isn't as straightforward as a communication thing, where if you're communicating between processes, it doesn't matter if they're on the same system or on different systems, it kind of works the same. But relying on a physical piece of shared memory requires the processors to be, and the processes to both be on that hardware that has that memory that's shared. Okay, so that's all I wanted to cover for today. I went through that pretty quickly. I would suggest you maybe play around with some of those things a little bit. Try that source code that we went through in here. And other than that, stay safe. We've got a few more things to go through this semester and a few more labs that we're going to do. So I want to make sure we get through all those. We lost a couple classes due to snow and a couple classes due to the midterm and the study for that. So we're going to have lectures pretty much every time. We will also have some assignments that get posted, so keep an eye out for those. And other than that, stay safe, and I'll see everybody next time.